Hi everyone. In this video we discuss how to find various equations of lines and planes in 3D space. The first topic is vector equation for lines. So assume that we have this coordinate system and there are two distinct points in 3D space. Here is point 1 and here is point 2. Any two distinct points in 3D space determine only one line between them. So here is the line passing through points P1 and P2. Now let's assume that point P is any point on the line, and here is point P. We can define different vectors for each one of these 3 points. This will be vector R1, this is vector R2, and this will be vector R. Now we can define a new vector, vector A, which is R2 minus R1. So this will be vector A. We see that vector A is parallel to vector R minus R2, and this is R minus R2. It's clear that vector A and vector R minus R2 are parallel to each other. So we can say that R minus R2 is some constant multiplied to R2 minus R1, which is the definition of parallel vectors. Let's say that points P1 and P2 are as follows. This equation implies that the vector equation for the line L is R equals R2 plus TA, where vector A is R2 minus R1. In this equation, the scalar T is called a parameter, and the non-zero vector A is called a direction vector. And the components of the direction vector A are called direction numbers for the line. There are alternative forms of the vector equation. Since r minus r1 is also parallel to the line, an alternative vector equation for the line will be r1 plus ta. These are also equations for the line where k is a non-zero scalar. The next topic is parametric equations. We just saw that vector r is defined as the summation of vector r2 and t times r2 minus r1. Let's say that our points have the following coordinates. Then R1 and R2 will be from here. We can write this equation as xyz, which is vector r, x2, y2, z2, which is vector r2, t times vector x2 minus x1, y2 minus y1, and z2 minus z1. This is also equal to in which each component are equal to each other, and y is equal to this term, and also z is equal to this one here. By equating the components, we will have x equals x2 plus a1t, where here a1 is the first component of vector a, where vector a was r2 minus r1. Then y will be equal to y2 plus a2 times t, where a2 is the second component of vector a, and z is equal to z2 plus a3t, where a3 is the third component of the vector a. These equations are called parametric equations for the line through P1 and P2. And in these equations, since t changes from minus infinity to positive infinity, we can think of it as point P changing its position on this line L. And if the parameter t is restricted to a closed interval, then the point P traces out a line segment starting at the point corresponding to the beginning of the interval, and then the ending at the point corresponding to the end of that interval. For example, in here, if t changes from -1 to 0, then start point of point P corresponds to t equals to -1, and its end will be t equals to 0. And from this equation, if t is equal to -1, then we will have r minus r2 is equal to minus r2 minus r1. Then the vector r will be equal to vector r1, which means that this point P, will be here at the location of point P1. And what if t is equal to 0? Then here we need to write 0 instead of t. Then the right hand side will be equal to 0 and vector r will be equal to r2, which is point 2 here. The next topic is symmetric equations. As we just say, these equations are called parametric equations. So we can observe that we can clear the parameter t by writing the following equation. This equation is valid if and only if the three direction numbers a1, a2, and a3 are non-zero. Then the resulting equation will be this one, which is said to be symmetric equations for the line through points P1 and P2. The next topic is vector equations for planes. We know that through a given point P1, there pass an infinite number of planes. So let's say that this is point P1, then this will be one of the planes. This one also can be another plane, and in general there will be an infinite number of planes passing through point P1. However, if we define a vector n in addition to point P1, then there will be only one plane containing the point P1 with the normal vector n. So let's say that this is plane P. This plane can be defined with point P1 and also the vector normal to plane P. So if we have a point P and we say that point P is any point on this plane. Now if vector R is OP and vector R1 is OP1, then this will be R minus R1, which is in the plane. So now we can form a vector equation of the plane. This will be the vector equation of the plane. And as you know here, vector n is perpendicular to vector r minus r1. So since these two vectors are perpendicular, then the dot product of these two vectors will be equal to 0. So as I said, this equation here is the vector equation of the plane. Now let's define vector n and points P and P1. Now with these definitions, we can find this dot product to be equal to, which is known as a Cartesian equation of the plane containing point P1. This is also sometimes called the point normal form of the equation of a plane.